Wind engineering is a subset of mechanical engineering, structural engineering, meteorology, and applied physics to analyze the effects of wind in the natural and the built environment and studies the possible damage, inconvenience or benefits which may result from wind. In the field of engineering it includes strong winds, which may cause discomfort, as well as extreme winds, such as in a tornado, hurricane or heavy storm, which may cause widespread destruction. In the fields of wind energy and air pollution it also includes low and moderate winds, as these are relevant to electricity production, dispersion of contaminants. Wind engineering draws upon meteorology, fluid dynamics, mechanics, geographic information systems and a number of specialist engineering disciplines including aerodynamics and structural dynamics. The tools used include atmospheric models, atmospheric boundary layer wind tunnels, open jet facilities and computational fluid dynamics models. Wind engineering involves, among other topics, wind impact on structures, wind comfort near buildings, effects of wind on the ventilation system in a building, wind climate for wind energy, air pollution near buildings. Wind engineering may be considered by structural engineers to be closely related to earthquake engineering and explosion protection. Some sports stadiums such as Candlestick Park and Arthur Ashe Stadium are known for the strong, sometimes swirly winds, which affect the playing conditions. History. Wind engineering as a separate discipline can be traced to the UK in the 1960s, when informal meetings were held at the National Physical Laboratory, the Building Research Establishment and elsewhere. Wind comfort. The advent of high-rise tower blocks led to concerns regarding the wind nuisance caused by these buildings to pedestrians in the vicinity. A number of wind comfort and wind danger criteria were developed from 1971, based on different pedestrian activities such as sitting for a long period of time, sitting for a short period of time, strolling, walking fast. Other criteria classified a wind environment as completely unacceptable or dangerous. Building geometries consisting of one and two rectangular buildings have a number of well-known effects. Corner streams, also known as corner jets, around the corners of buildings. Through flow, also known as a passage jet, in any passage through a building, a small gap between two buildings due to pressure short-circuiting. Vortex shedding in the wake of buildings. For more complex geometries, pedestrian wind comfort studies are required. These can use an appropriately scaled model in a boundary layer wind tunnel, or more recently there has been increased use of computational fluid dynamics techniques. The pedestrian level wind speeds for a given exceedance probability are calculated to allow for regional wind speed statistics. The vertical wind profile used in these studies varies according to the terrain in the vicinity of the buildings, and is often grouped in categories such as exposed open terrain with few or no obstructions and water surfaces. Its serviceability wind speeds. Water surfaces, open terrain, grassland with few, well-scattered obstructions having heights generally from 1.5 meters to 10 meters. Terrain with numerous closely spaced obstructions 3 meters to 5 meters high, such as areas of suburban housing. Terrain with numerous large, high and closely spaced obstructions, such as large city centers and well-developed industrial complexes. Significance. The knowledge of wind engineering is used to analyze and design all high-rise buildings, cable suspension bridges and cable-stayed bridges, electricity transmission towers and telecommunication towers and all other types of towers and chimneys. The wind load is the dominant load in the analysis of many tall buildings, so wind engineering is essential for the analysis and design of tall buildings. Again, wind load is a dominant load in the analysis and design of all long-span cable bridges.